In this video I want to talk about binomial distribution. We're going to do a bit introduction to it, and we're going to talk about the formula and how it works. Alright, so let's do a little bit of a story here. So I have a man here, and every day he walks under this tree. Maybe on his way to work, there's a tree there, he has to walk under it. There's a bird that lives in the tree, and the bird sometimes poops onto the man's head. Now, from experience, he knows that it happens about, let's say, 20% of the time. So, 20% of the time, he gets pooped on. And, yeah, I don't know, how many times will he get pooped on in the next 2 weeks? Something like that. This is a classic binomial distribution. There are a couple of things that make it a binomial distribution. First one, there are n independent trials. N is like the number, so there might be 10, there might be 20, there might be 50 independent trials. They're independent trials because the probability doesn't change from trial to trial to trial. For instance, if you've got a pack of cards and you pull one out and then you put it back in, the probability of pulling out a different card or the hearts on the second trial is the same as the first trial because you replaced it. However, if you put it in, took it out, and then put it away, the probabilities change, so they're not independent trials anymore. These are independent trials as well. The probability is the same every single time, and it's not dependent on whether he got pooped on. He's just as likely to get pooped on yesterday as today as tomorrow. Independent trials. Alright, there are two possible outcomes, success or failure. That's why it's called a binomial distribution, because there are only two things that can happen. Either he gets pooped on or he doesn't get pooped on. Because I'm being a bit perverse here, we're going to say that getting pooped on is a success and not getting pooped on is a failure. Doesn't matter which one you call success or failure, everything still works the same. And then there's a third thing that makes it a binomial distribution. For it to be a binomial distribution, the probability of success has to be fixed. That means that it's a 20% probability today, it's a 20% probability tomorrow, it's a 20% probability the next time. If the probability changes day to day or from trial to trial, then the probability of success is not fixed, it's changing. So those three things have to be true for it to be a binomial distribution. If any of those aren't true, it is not a binomial distribution. Let's do a question. So here's our question. What is the probability he gets pooped on exactly twice in the next 4 days? Now, a bright Year 8 student can probably do this kind of question, and they do it using a tree diagram. So there is my enormous tree diagram for this. The first day, the second day, the third day, and the fourth day. And we want to know what is the probability he gets pooped on exactly twice in the next 4 days. Alright, so let's see. That's him getting pooped on 4 times. That's him getting pooped on 3 times. This one is 3 times. Alright, this is one of the ones we want. Okay, so that's poop, poop, no poop, no poop. Alright, I'm just going to draw in some probabilities on that one. We know that there's a 20% chance he gets pooped on there, a 20% chance he gets pooped on there, an 80% chance that he doesn't get pooped on, and an 80% chance that he doesn't get pooped on there. And I can find that probability by doing 0.2 times 0.2 times 0.8 times 0.8. So when I do this times this times this times this, I get 0.0256. So there's a 2.56% chance that he gets pooped on, not pooped on, and then not pooped on in that order. But there are other ways to get exactly pooped on exactly twice as well. For instance, poop, not poop, not poop. This is another example of a success, I guess, of this happening, of getting pooped on exactly twice. So that's going to be 0.2 times 0.8 times 0.2 times 0.8. Well, what do you notice? 0.2, 0.8, 0.2, 0.8, and the other one was 0.2, 0.2, 0.8, 0.8. Because the probabilities aren't changing from trial to trial, we get the same probabilities every single time. I don't need to put that into my calculator because multiplying all those numbers and multiplying all those numbers are going to give me the same answer, 0.0256. Now, I just need to go through this whole tree diagram and find all of the times when it happens exactly twice. So I think I've got them. Poop, not poop, not poop, poop. So that one's one of them. Another one would be not poop, 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 not poop. So that one. Another one would be not poop, poop, not poop, poop. That one. And the last one would be not poop, not poop, poop, and poop. So there are 1, 2, 3, 4, 5, 6 different paths in our tree diagram to get pooped on exactly twice in the next 4 days. If I want to know the probability of this or this or this or this or this or this happening, I just need to add all of those together. Obviously, a faster way to do it will be to take one of them and multiply that one by 6. Alright, so I get an answer. 0.1536 is my answer. That is the end of the question. The way that a year 8 student would do it. We've got a better way, but this is the way a year 8 student would do it. And if they knew a little bit about probability notation, they would say that the probability of x is equal to 2 is equal to 0.1536. Okay, now let's do it the year 12 way. So here's my formula. The probability that the variable x is equal to x, in this case, the probability that the number of times we get pooped on is equal to 2, is equal to, this says NCX, so superscript N, C, subscript X, PX, P to the X, Q to the N minus X. Alright, so probably need a few little bits of information about how to interpret that formula. NCX is just the number of ways. The number of ways it can happen. Alright, so in this case, the number of ways it could happen was 1, 2, 3, 4, 5, 6. And we have a handy way to figure that out. I'll show you that in a minute. So that's what that is. Now, P to the X. P is the probability of success. Now, in our case, the probability of success was 0.2. The probability of getting pooped on was 0.2. Now, Q, I'll come back to X in a minute. Q is the opposite of that. It's the probability of failure. Probability of failure. Now, because it's a binomial distribution, these will always add up to 1. 0.2, adding to that, 0.2 is the probability of success, so 0.8 was the probability of failure. And now we can do all of that. N was the number of trials, and X is the number of successes that we want. So now I can do this question all without drawing a big tree diagram, just by using that formula. Alright, so I'm going to use my formula over here. So the probability that X equals 2 is equal to NCX. N is the number of trials, so I'm having 4 trials. C, 2 is the number of successes, so 4C2. P, probability of success, 0.2 to the power of X, that's the number of successes that I want. I want 2 successes, times Q, the probability of failure, 0.8, to the power of N minus X, to the power of the number of trials, 4 minus 2. Okay, that's the formula. Now, 4C2, take my word for it, 4C2 is 6. There's a button on your calculator that will tell you what 4C2 is, and I'll show you some other ways to do it as well. Now, 0.2 squared, that's 0.2 times 0.2, which is exactly what we did here, 0.2 times 0.2. It's 0.04. And now we have 0.8 to the power of 4 minus 2, which is 0.8 squared, which should be 0.64. And that 0.8 squared is just 0.8 times 0.8, so that happened there. So what our formula says is 6 times, and 6 is the number of ways it happened, times 0.2 times 0.2, that's the number of successes that happened, times 0.8 times 0.8, that's the number of failures that happened. Put that all into your calculator and you'll get the same answer I had there, 0.1536. Okay, that is your big introduction to binomial distribution. I've left a little bit of a mystery as to how you figure out what 4C2 is, but next video for that one. You've got a handy little formula that basically does a whole bunch of Year 8 work. Why would I need a handy formula when I have a tree diagram? Well, if we had 8 trials, or 20 trials, or 50 trials, your tree diagram is going to get exceptionally large, and you're going to end up in a lot of trouble. Binomial distribution, that's the introduction, that's the formula.